Hello, this is going to be the dry lab version of Chemical Equilibrium Week 1. The first thing you want to make sure of is that you take the third cumulative assessment, aka the quiz. Your instructor will provide you with a link for that. If you are in one of my lab sections, you can find that link right on Blackboard in the announcements section. So here's how we're going to do this dry lab. I'm going to walk you through the majority of what we would have done in lab and talk about it as we go. There is a handout that goes along with it that you can follow along on with me. What I would suggest to you is as you go, try to pause the video and see if you can predict the answer to a question and then resume the video. That's going to be a pretty good way of making sure that you understand concepts as we go. So what we're going to talk about is the definition of chemical equilibrium. It means something specific in chemistry. And then the rest of the lab is predominantly going to be talking about stressing something at equilibrium and then how it responds to that. So we'll walk through a series of reactions, and then after that, there's going to be some follow-up questions, some of which will be covered in the material that we're about to talk about. So you'll be that much farther ahead of the game. All right, so let's introduce chemical equilibrium. Let me move myself. Go. Okay. All right, so let's start with a reaction. Here's a sample reaction where two ions come together and make a bigger ion, and this is in water. So the first one, Fe3+, is iron. The second one, SCN-, that is called thiocyanate ion, and then the product that it makes is called iron thiocyanate ion. The ion on the product side right here has a color. It's got this red color. So up until now, we've sort of been telling you that once reactants make products, that's the end of the story, but it's really not. So what happens is when the reactants make a product, they have to collide with each other. They have to hit each other under the right set of circumstances, according to collision theory. So what happens is these are all floating around together in water. The two reactants are making the product, but as the product is floating around, it can collide with another particle and turn back into its original reactants. So we have two reactions going on in the same container. Now reactions go at different rates, but what happens is when you have a reaction going forward and backwards, they can reach a point where they are happening at the same exact rate. So the way we show two reactions that are opposite, forward and backwards, is using this double arrow right here. When a forward and a backwards reaction are happening at the same rate, we call that chemical equilibrium. So it means opposite reactions happening at the same rate. So graphically, when something hits equilibrium, it's going to look like this. So here's a graph showing the amount in terms of concentration of the two reactants. And so let's just say at the beginning, at time 0, we don't have any of the reactants present. I'm sorry, we do have reactants present. We have some amount of reactants present. Thinking ahead of myself. And then we have 0 products present. Okay, so now we let the reaction go. So the reaction goes and it starts to make some product. Now you can't just make product out of nothing. You have to use up some of your reactants. So as the product starts to go up, the reactants start to go down. And this continues, at least for a little while, because what eventually happens is the curves start to straighten out. So the product starts to get made, but the upward trend doesn't continue forever, because what happens is as you make more product, you have more particles there. And according to collision theory, if you have more particles, you have a faster rate of reaction. So the backwards reaction starts to catch up to the forwards one. And so the amount of the reactant that we're losing starts to slow down until we've reached a point where the rates of the forward and backwards reactions line up. And so at that point, when the concentrations stop changing, we have hit what we call chemical equilibrium. So same exact concentrations over time. They're not equal to each other. It's just that the concentrations aren't changing anymore. So To us, if you looked at a reaction at equilibrium, you really wouldn't see very much. It would look just like this. This is actually a picture of that reaction happening at equilibrium. It doesn't look like anything to us because if the forward and the reverse reactions are happening at the same rate, there's no net change in the system. It's kind of like if you were in a boat and it was leaking water and you're bailing the water out, but you're bailing it out just as fast as it's coming in. The amount of water in your boat isn't going to change. The water line isn't going to change. But that's not to say that the water isn't churning in and out. And that's what's going on here. So to us, it doesn't look like the reaction's happening, but the particle level, it is. The reaction's going back and forth. Okay, now what we're going to talk about is what happens when you have a system at equilibrium and you start messing around with it. So we can mess around with it by adding some more of one of the reactants. We can add some more of one of the products. We can remove them. There are lots of different ways that you can disturb something at equilibrium. So this is a picture of 4 of the same exact reaction, just in these 4 different containers or wells. This is called a well plate. The first one is going to be the control. So let's go to the handout. Move myself. Okay. There we go. Okay, so this is the first page of the handout, and you can see that we have this chemical equation we were just looking at, and what I'm going to start to do is just paste some pictures in as we go. So the first one we've got is the control. So it has this orangish color, and what the color is telling us is what ions are present. Now, the product here has a reddish color, so that you can see that this has a bit of a reddish tinge to it. And the other ion here, the iron, has an orangish tinge to it. The SCN does not have much of a color at all. So, down here, when we have nothing going on there, our control, it's got a color that is, let's call it orange-red. Now what we're going to do is start to mess around with it. So the next thing we're going to add to it, the stress we're going to impose on it, is going to be adding some Fe3 plus and NO3 minus. So if you do that, if you put some Fe3 plus in there, the NO3 minus is there, but it's not doing anything, it's spectating. So it's really the Fe3 plus that's doing something. So if we put that in there, what you're going to see is that when you add Fe3 plus, it's going to turn more red. So the color becomes more red. Now, let's think of what we did to the equilibrium here. We messed around with the rates of the reactions. So here we are, and when we add Fe3+, what we have just done is we took this and flooded it with more of something that's already there. There's already iron 3+ there, and we just put more in there. So if you remember back to collision theory, if you have more particles present, it's more likely that the iron is going to run into the SCN. And so what does that do? It speeds up the rate of the reaction going to the product side. So what happens is you make a little bit more product, and then once you make that product, then the reaction going backwards starts to catch up again until it reaches equilibrium. So it's not where it was at the beginning, but it's at a new state of equilibrium, because what we define that as is opposite reactions at the same rate. They don't necessarily have to be at where they were at the beginning. So that's what happens. So what we do the equilibrium? We added a reactant. And so which reaction was faster? Well, we can call it the reaction going forward. We can call it the reaction going to the right. There's different ways of saying this, but this says forward or reverse. So we'll say forward. So the term for this is we say that the equilibrium shifts. So in our case, it shifts to the right, shifts forward. And so as a result, what we saw happen was we made a little bit more product as a result of that happening, as a result of the shift. So the response to the stress was it made more product. All right, so that's what's going on here. So let's look at another situation. Now what we're going to do is we're going to add NaOH. This is a little bit different because we're not adding something that's already there. What we're going to be doing is taking away something, and I'll talk about that in a second. So here's the picture of it. So when you add NaOH, what this does is the OH, more specifically, the hydroxide ion, it binds with the iron ion right there, and it effectively removes it from this equilibrium. It makes it no longer available. So now what happens is, if there's less of the iron, it's less likely to run into an SCN ion. So what it does is it slows down the reaction going forward. So the reaction going forward slows down, and then by default, the reaction going backwards is now the faster one. It doesn't speed up, it's just that now it's faster than the forwards reaction. So what we see is that you can see that the reddish part of the color there kind of faded away, and now it's a little bit more yellow. And what we know is that the yellow color is associated with the iron ion right there. So the color is, let's call it less red. What did we do to the equilibrium? We removed a reactant. And so which reaction is faster? The one going backwards is faster by default. It doesn't speed up. It's just that it's faster than the forward reaction. So which reaction is faster? Reverse. So we say that this equilibrium shifted backwards or shifted to the left. So then the response to the stress, I'm going to move myself. The response to the stress was it made more reactant. Another way to say that is we made less product. Same thing. So overall, what you can see happening here is that when we disturb an equilibrium, it responds in a certain way that we can generalize. So when we add a reactant, it responded by making more product. Add reactant, make more product. When you remove a reactant, it makes more reactant. So what the general idea here is when you have something at equilibrium and you disturb it, what it does is it responds or shifts in a direction that minimizes the stress that you put on it. It basically compensates for what we do to it in order to reestablish equilibrium. So in general, we can put it together as follows. So when a system is equilibrium, when you stress it, what it does is it responds, shifts, we say, in a direction that minimizes the stress. Okay, now let's use it. So down here, we have one last situation. So what we're going to do here is we're going to add K plus and Cn minus. So this is dissolved in water. So we have K plus ions there, we have SCN minus ions there. The K plus is just a spectator, it's not doing anything. The SCN though, if you go back to the chemical equation right here, what we're going to be doing is adding more of this SCN ion. So what will this do to the equilibrium? We are going to be adding more reactant. And so now what I want you to do is try to predict when you add more reactant, what's going to happen to the rate of which reaction is going to be faster. Is the reaction going forward going to be faster? Or is the reaction going backwards going to be faster? So maybe pause the video and predict. Okay, so the forward reaction speeds up because it's just more likely for an SCN to hit an Fe, and that speeds up the reaction. Okay, predicted color change. So the way we're thinking of it is, does it become more red or less red? So what we would predict is that if the forward reaction goes a little faster, we're going to make a little bit more product, and then the product can catch back up until the rates are equal. So overall, what we're going to say is that the color change is going to become more red. And so I'll show you a picture of it. Let me grab that. Here we go. So the actual picture of it. Oops. There it is. So indeed, it does become more red. We disturbed it at equilibrium by adding a reactant. It responded by making more product, and so that's why the color becomes slightly more red. All right, now what happens is, let me go back to this. So what happens is when something's at equilibrium, the concentrations aren't changing. But then when we disturb it, one of them does change. So let's say that we disturb it in the way we did for the first time. So we disturb it by adding some iron ion. So you can see that this jumps up dramatically. And then what happens is the forward reaction is going faster. So we make a little bit more product. And in order to make product, you got to lose some reactant. So that swoops down, and so does the other reactant, until eventually the rate of the backwards reaction catches back up and it reaches equilibrium once again. And so what is happening here is that now the concentrations are no longer changing. Oops. They're not changing anymore. And what we can get out of this mathematically is a constant, because these are not changing. We have some proportions going on, and we can get a constant out of it. So let's take a look at that. So this is what we call the equilibrium constant. This is a number that you can get out of a system at equilibrium that will tell you which of the reactants or the products, who's present in more amount. So the way you set it up is if you have a chemical equation that looks like this, where you have reactants, products, and then each one has a coefficient. The equilibrium constant is symbolized with capital K, and it's set up by calculating this fraction, numerator, denominator. And we're talking about concentrations, so that's what the bracket right here means. The concentration of whatever is on the inside. We're going to raise it to the power of whatever its coefficient is, and because that's how we get a constant out of this numerically. And then we're going to divide it by the concentration of the reactants raised to whatever power their coefficient is. So if we have this chemical equation right here, so here's the coefficient for A, the coefficient for B, the reactants go on the bottom, the products go on the top. We raise them to whatever power the coefficient is. And then we're going to be multiplying if there's more than one reactant or product on the same side of the fraction. All right, so here's the one we just looked at. So all we're going to do is just set it up. That's all. We'll talk about calculating it a little bit later. So on the top, we have a product. So there's our product, FeSen2+. We have brackets meaning concentration. And then we have two reactants. So we have Fe3+, and then we have SCN-. And because everything has a coefficient of 1, that just means that we don't need to put an exponent up there. They're all exponents of 1. So that's how you set it up. This is known as an equilibrium constant expression, an equation. Okay, so let's look at another situation. Let me scoot down here a little bit. Okay, so this one is going to be acetic acid in equilibrium in water. So what's going on here is we have this molecule right here is acetic acid. CH3COOH, this is the acid that's in vinegar. It's dissolved in water. And then what happens is this molecule breaks up, dissociates into two ions. This ion right here, CH3COO-, is called acetate. That's why the acid's called acetic acid. And then we have this ion right here, which we'll be talking about quite a bit in a couple weeks. This is the H+ ion, aka a proton. And this is all in water. So the first thing we can do is set up the equilibrium constant expression. So we have two products this time on the top. So we have CH3, COOH, and then we have a minus, and that's all set. So for this one, we are going to be looking at a change in color. However, this reaction itself doesn't have a color, so we're going to be adding something extra to make it change color. So what we're going to add to it, is an indicator that's called methyl orange. So it changes color in between red and yellow, and when it goes from red to yellow, that's telling us that the amount of H+ ions have changed and they've decreased. When it goes the other way, when it goes from yellow to red, it means that the amount of H+ ions has increased. So let's look at just the baseline one. So when you have this with the methyl orange in it, and you haven't disturbed it yet, it has this color, kind of orangey, maybe a little bit of yellow in there. So it has this baseline color. And then what we're going to do is we're going to stress it by adding sodium acetate. So when you add sodium acetate, what you're really adding are sodium ions and acetate ions. Acetate is CH3COO minus. So you can see that the color changes from reddish to yellow. So the color change is red to yellow. And so what happened to the amount of H plus after we added it? Well, this table says that when you go from red to yellow, the H plus ions have decreased. So those decreased. And so what we did was we added CH3COO minus. Let me bring it up here for a sec. We added CH3COO minus. That's one of the products. So by adding more product, we speed up the reaction going backwards. And that's simply just because there's more there and it's more likely that they're going to collide with an H plus ion. So that explains why it responded in the way that it did. So when we added that, was a source of extra acetate ions, what did it do? You added more product. And as a result is it shifted backwards. The reaction going backwards speeds up. And in order to go backwards, in order for this reaction to go backwards, you have to use up a little bit of your H plus. So that explains why the H plus goes down. So direction in which equilibrium shifts is, we'll say backwards or to the left. And that's what happens with that one. Okay, moving along. We are on our second one. So this is our second situation of a reaction at equilibrium. And what we've got here is sodium chloride, table salt. And what it's doing is solid sodium chloride is dissociating into two ions, Na plus, Cl minus, dissolved in water. That's what the AQ means. And then the solid is not dissolved in the water. So here is how we set up the equilibrium constant. We have Na plus times Cl minus, and then on the bottom we have NaCl. There we go. But there's a little bit of a problem here. When we are talking about brackets around a substance, we're talking about its concentration. And in order to have a concentration, you have to be dissolved in something. Now, a solid is not dissolved in something. If it were, we would have AQ right here, but we don't. So that means that a solid doesn't have a concentration just because it's not dissolved in water. These two do because they are dissolved in water. So there is an exception to the equilibrium constant expression, and that is that pure substances such as solids and liquids are excluded from the equilibrium constant expression. So we're just going to update it. And really all that's going to happen is this part of the expression is just going to be left out. So all we're doing is just writing what's left over. So Na plus, Cl minus, and there we go. So that's one exception. There is another one. So one exception are solids. Okay, so we have a system at equilibrium. We have NaCl solid, Na plus, Cl minus. So what it looks like is salt water, right? NaCl minus in water is salt water. So it's not the most colorful thing in the world, but this will be our control. So what this is just salt water. Then what's going to happen is we're going to stress it. So let's talk about that. We're going to stress it by adding hydrochloric acid. Hydrochloric acid is HCl. And what we're doing with it is we are going to be adding one of the ions that's already there. So when you add hydrochloric acid is HCl. And in water, it's not really HCl, it's H plus and Cl minus. So what we're doing is we're adding more of an ion that's already there, Cl minus. We're adding more product. And what we see happens is you can see that some solid comes out of the solution. So we make some salt, some solid salt. So the solution gets cloudy or precipitate forms. And the reason for that is we formed reactant, solid NaCl. The HCl was a source of extra chloride ions. What did it do? So what that effectively did was it added more product and it gets the backwards reaction to speed up. So what we did was we added more of a product. And so the direction in which it shifts, again, back to rates, is that if you add more product, it's going to be more likely to hit this ion, and the reaction going backwards is going to be faster temporarily until the one going forwards catches back up again. So the direction in which it shifts is going to be backwards. All right, so that's the second one. Hopefully you're getting the hang of it at this point. Once you've done it a couple times, it's actually not terribly complicated. All right, the next one has some pretty interesting color changes. This one is a system at equilibrium involving a chromate and dichromate ions. Each ion has a distinctly different color. Chromate is CrO42-, and what it does is if it combines with two protons, two H+ ions, we get these two products. We get water, and then the other product is this dichromate ion. So the difference in color is dramatic. The chromate has a yellow color, and then the dichromate has an orange color. So the first step is to set up the equilibrium constant expression. So in here we have two products, CR2O7, 2 minus water, CrO42- with a 2 up there because there's a coefficient of 2, and then we have 2H+, so we have H+, and then we have a 2 because that's what its coefficient is. Now, there's an issue with this one as well, just like in the last one where we couldn't include the solid because it wasn't dissolved. Well, when you have a concentration of a substance, it's dissolved in something. So when you're dissolved in something, you are the solute. In this case, everything's dissolved in water, and in this case, water is the solvent. So having a concentration of water doesn't really make sense because that's not the definition of a solute is not a solvent. So for this equilibrium constant expression, what we can do is rewrite it, but just exclude the part with water. There we go. So the second exception to equilibrium constant expressions are solvents. Most of the time it's going to be water, so usually if you see water, that's something that can be excluded. All right, so now we're going to talk about stressing it. So when you have just the system at equilibrium, it has more or less, more or less a yellow color. Not doing too hot right now. There it is. Excuse me. Okay, so this is what it looks like as a baseline. This is yellow. You can see that the yellow, that's the chromate ion. There isn't too much dichromate ion there. Now what we're going to do to stress it is we are going to add to it some sulfuric acid. So sulfuric acid, what it does is it adds more H+ ions. When you add that, what's going to happen is it changes into an orange color. Okay, so let's think through this. It became orange. So the color changed when sulfuric acid was added. Let's say yellow to orange. The H2SO4 was a source of extra H+ ions. How does it shift the equilibrium? Okay, so we add more reactant, more likely to hit chromate, and so the reaction going forward speeds up. So it shifts it forward or to the right. Now we have another situation in which we're going to stress it. We're going to add sodium hydroxide to it. So when you take the yellow one, the original yellow one, when you start with the orange one, if you start with this and then we add some NaOH to it, what we see is that when you add NaOH, it goes from, let's say, orange to yellow. And if we think through this one's a little bit different. Color change when NaOH solution was added. It goes from orange to yellow. The hydroxide ions in the solution removes one of the ions. Which one did it remove? Okay, So we have OH minus, and it's going to be taking away one of these. And your first guess would probably be right if you take a look at these. The ion it's going to take out is going to be H plus. What it does is it combines with it and makes water. So effectively what happens is we are removing H plus. So removing H plus. What does it do to the equilibrium? Well, if you're taking out a reactant, it's going to slow down the reaction going forwards. So by default, the one going backwards is faster. So what does it do to the equilibrium? It slows forward reaction. And then direction in which it shifts is reverse or to the left. So again, what we did was we removed a reactant. The reaction going forward is slower. The one going backwards is now the faster one. And so if we remove this, it's going to compensate by making a bit more. And one of those that we're going to be making a bit more of is the yellow ion. And that's why it became more yellow. Okay. Now, the last system in equilibrium, and then we're going to talk about calculating the value of K. This one are gases. Now, up until now, we've looked at ions that are dissolved in water. This one is going to be a gas, and the gas is NO2. And what happens is, if two NO2 particles hit each other, they make a bigger molecule. The term for this is dimerize. The two molecules hit each other, and we make N2O4, which is really two NO2s that are stuck together. There is a pretty dramatic difference in the color. When you have NO2 by itself, the color of the gas is brown. When you have N2O4 together, it has no color at all. So we can set up the equilibrium constant expression. Now, gases can mix with each other, so we can therefore talk about them having concentrations. So for this one, we have N2O4. There's no coefficient there. And then down on the bottom, we have NO2. And now we have a coefficient right here of 2. So that is going to go right there. Okay, let me show you a picture of it. What we're going to be looking at for this one is changing the temperature. We're not going to be adding or removing a reactant or a product. Well, not really. So what you can see is, here's this tube that's filled up with this system at equilibrium. On the left, the flask is heating up a water bath, and that's heating up the tube. And then over on the right, we have the same tube, but in an ice bath. So one's being heated, the other's being chilled. So the stress that we're going to impose on it is changing the temperature. Higher temperature and lower temperature. So when you have higher temperature, do we have more NO2 or less NO2? So the higher temperature is more brown. The brown colored gas is NO2. So we have more of it. So we have more NO2. And so if we have more NO2, what that's telling us is when you heat it, it gets the equilibrium to move in a direction that makes more of it. So it shifts it backwards to the reactant side. Direction in which equilibrium shifts is reverse, or another way to say that is to the left. On the other hand, when you cool it, we're going to see the opposite effect. So when you cool it, the temperature goes down, and you can see that the color is less brown. It's not as brown as it was. It doesn't turn totally colorless because there's some NO2 still in the tube, but you can see that the color is less brown. So that's telling us that we have less NO2, and so the direction in which it shifts is going to be forward or to the right. So we've manipulated temperature, and that's causing the equilibrium to shift in a certain direction depending on what we're doing to the temperature. Increasing the temperature makes it shift to the left. Increasing the temperature makes it shift to the left. Decreasing the temperature makes it shift to the right. Now, what we can do from this is we can figure out if this reaction going from here to here is exo or endothermic. The way we do that is conceptually we think of heat as a reactant or as a product. So what we know, let me move this in a spot where we can kind of see everything. What we know is that when we add heat, when we increase the temperature, when we add heat, we make more NO2, it goes to the left. So adding heat makes equilibrium go to the left, Removing heat makes the equilibrium go to the right. So one of these scenarios will be true for both cases. We can either treat heat like a reactant or a product. So if we add heat, that would be sort of like we're adding a reactant. If we add a reactant, that's going to make the equilibrium shift to the product side, and it would become less brown if we heated it. But yet we know that the opposite's true. When we heat it, the equilibrium shifts backwards. So this situation, treating heat like a reactant, is not working. If we treat heat like a product, if we add more heat, what that is going to do is it's like adding a product, so it's going to get the equilibrium to shift to the reactant side, which is the brown side, and so we see a deeper color forming. If we remove heat, it's like we're removing a product, and so the equilibrium is going to shift to the right to make more of it. So should we treat heat as a reactant or a product? Well, in order for this to work, we would need to treat it like a product. And so based on that, conceptually, when heat is on the reactant side, the reaction is endothermic. When it's on the product side, the reaction is exothermic. So based on the fact that it's on the product side, then we can say that this reaction is exothermic. A slight nuance here is that there are actually two reactions going on, forwards and backwards. So when I say the reaction being exothermic, what I really mean is that the reaction going from the left to the right. So I'm talking about the forward reaction is exothermic. The reaction going backwards is endothermic. Okay. Last thing we're going to do is talk about how you calculate the equilibrium constant, the actual value of K. So we're going to revisit the first equation the first chemical reaction we looked at. So the goal here is to calculate the numerical value of the equilibrium constant, and then we'll talk about how you can interpret it. So here's the same chemical equation from the beginning: iron thiocyanate, iron thiocyanate ion. Here we have the equilibrium constant expression set up. Okay, so let's just start making up some numbers. Let's say that we have some starting concentrations. So we have a starting concentration of Fe3+ in molarity. We have a starting concentration of SEN in molarity. And if you haven't seen this format before, this is just scientific notation. 6 times 10 to the -4. So these are decimals. And then we have no product at the beginning. So in order to calculate K, what we need are these three concentrations, but they have to be at equilibrium. So the way that we would have done this in lab is that to figure out the concentration, we talked about how that ion, this product right here, is red. So what we can do is we can generate a graph of concentrations versus absorbances. And this was something that we did last semester. So if we measure the concentration of FeSCN2+ and plot it against absorbance, we get a straight line. That's called a calibration curve. And this is according to Beer's law, which says that absorbance and concentration are directly proportional to each other. And the purpose of that is, if we know the absorbance, we can go backwards and calculate what the concentration is. So let's say that we made a calibration curve, and we have this information from it. So this is data. This is the slope of the line. It's 1470. This is the y-intercept. And then we have our mixture. And let's say that its absorbance is 0.274. The goal here is to calculate the concentration. On this graph, it's on the x-axis. So using the equation y = mx + b, we are calculating the x value. So let me bring up a spreadsheet so that we can look at that. Let's see, here we go. Hide that. Okay, so we have an absorbance of 0.274. That's our y value. We have 1470. Whoops. We have 1470 for our slope m. We have an intercept of 0.07 b, and then our job is to calculate the concentration of FeSCN2+, which is going to be the x value. Okay, so here comes some algebra. We have y = mx + b. We want to get x by itself. So in order to get x by itself, what you have to do is you have to do y minus b, and then you have to divide by the slope. So that's exactly what I'm going to have Excel do. So I'm going to do y minus b, and actually I should put that in parentheses, y minus b divided by the slope. And there we go. So 0.00014. So we'll call that 1.4 e to the negative 4 moles per liter. Make sure I got my math. Yes. Okay. So that's the concentration at equilibrium. So now we knew where we started. We were just given these numbers. We've just calculated the equilibrium concentration of one of the substances. And for that one, it was 1.4 e negative 4. And so we need to get these other two concentrations at equilibrium. So the way we do that is we insert a row in the middle here. What it shows is we have where we start, where we finish, and then this is the change. So we have a table here that has initial, change, and equilibrium. So the name for these tables are ICE tables, initial, change, and equilibrium. The middle row right here is going to follow the stoichiometry. Everything is in a 1:1:1 ratio. So here's where we start. Right here, we start with 0 and we end up with this much moles per liter. And so the change is going to be that same amount, and it's going to be a positive value because positive means that it's gaining. Now going across, because molarity has moles in it, and these are mole ratios, molarity follows mole ratios. So in order to make a product, you got to lose a reactant. That's going to be minus, and that's going to be minus, and it's going to be minus the same exact number because they all have a coefficient of 1. They all have the same coefficient. There we go. All right, now I'll let you do the next parts. And what you're going to do here is just simple subtraction. So you're going to start with this number. The sign is going to tell you to subtract this number. So it's going to be 1 times 10 to the minus third minus 1.4 times 10 to the minus 4. You'll get your number right there. You repeat for this one, and then we've already got this one. Then, once you got that bottom row, you can plug and chug. You can plug in the concentration of the product and the reactants and get a value for K. What it's going to tell you, there's a way you can interpret this is a fraction, and we like to think of this number as being either bigger than 1 or less than 1. So if it's bigger than 1, that means that the numerator is bigger than the denominator, and on the numerator we have products. So that means that if this number is bigger than 1, then we have mostly products at equilibrium. And if it's less than 1, so if it's a decimal, it means that there are more reactants than products at equilibrium. So that's what that number tells us. It lets us sort of peek into the system at equilibrium and tell us, are there more reactants, more products present? And that sort of varies depending on the reaction you're looking at. Okay, so that about does it. And now let me show you the follow-up questions and what they're going to look like. So your instructor will provide you with these. So it's this document right here, and any place where there's a blue box is where you're going to fill something in. Now, this first table is just a summary of everything we just did. So you should see that if you followed along, you can just copy and paste these right into here. And then we talked about what stress we put on it and the direction it shifts. So that's something we already did. So then here you're going to put a definition of equilibrium. And then on to the second page, it's talking about a reaction and manipulating it and how to get more product. What does the value of K mean that you got earlier? How are concentration and absorbance related to each other? And then finally, you're going to have an ICE table. So it's going to give you a new one. It's got some numbers filled in for you. And so you're just kind of doing the same sort of calculation that you did earlier. Okay, so just to wrap up, so make sure that you complete and submit these follow-up questions. Your instructor will let you know of a due date. And then don't forget that we have this quiz number 3 to take. Otherwise, contact your instructor if you have any questions, and looking forward to hearing from everyone soon.